So most of the time when we're dealing with stress and strain, we often want to keep in the linear elastic region of our stress strain diagrams, right? We really like when we can use our modulus of elasticity. We really like that it lets us use things like our displacement equation that come from a combination of Hooke's law and everything being elastic. But this isn't always the case in our real world, right? Sometimes we want a little bit of plastic deformation because it does allow us to have additional carrying capacity, right? Like we could have a greater load if things deform plastically because they're able to take on more stress than is allowed in just our linear elastic region. So things that can work for us under this case, we usually call these materials, a special group of materials we call elastic perfectly plastic. Perfectly plastic, or elastoplastic. Elastoplastic materials are the ones that we would want to use in this case. Things that have a stress-strain diagram that look perfectly something with a Hooke's law linear elastic region and then just a straight yielding region on our stress-strain diagram. Or maybe they have that perfect linear elastic region and then maybe they go up so they can support some additional loading. But they have this nice yielding area, this very nice plastic deformation area where we can get a little bit of additional loading here, right? We go up from our proportional limit stress to some higher stress, get a little bit more loading, a little bit more strain, right? A little bit more deformation before failure. So we can think of something like if we have maybe, here's the ceiling and we've got this string hanging down from the ceiling that's held taut. It's a lamp or something is hanging down from the ceiling. But let's say we have two wires coming from this lamp. So one is held taut and then there's a wire that's a little bit longer. He's just a little bit looser, right? So when we have two members like this, one is being held taut and one is not being held taut at all. It's loose, it has extra room. Essentially, if we were to stretch that down, then our first guy here would start traveling up our stress strain diagram, right? He's taking on more and more stress, while our guy on the right here, number 2, is not taking on any stress at all. He's down here, right? He's loose, loosey-goosey, until to the point that he gets pulled taut, right? So he's loose, he has extra room. Our other guy is moving through the elastic region until both of them are pulled taut. And then what we have is we have our number 1 guy here moving up through into the yielding region, right? While number two here is now hanging out somewhere in the elastic region. So I can have one of my strings, even if they're made of the same material, one of them move into the plastic region, one move into the elastic region, and essentially it gives me this extra room. If I keep pulling and keep pulling, that I can max out one of my guys in the elastic region and then still have a guy in the plastic region because I've given myself this extra room with this elastoplastic material, where that would be my number 2 string and this would be my number 1 string who's now going under plastic deformation, while number 2 is maxing out his elastic deformation. So again, my number 2 string, he's in the elastic deformation. When I remove this lamp, I cut the lamp off, he's going to go back to the way he was before. All of that energy is recovered. He'll go back to his original shape. Whereas my number 1, he's stretched out forever now. He will never go back to his original shape. He's permanently deformed. But he did give me that extra load-bearing capability. He was able to hang on to the lamp for longer than if I was just trying to get it in the elastic region. So it can be really helpful for things like that. Plastic deformation does do some shielding for us against failure, right? We want things to deform plastically before they fail. It gives a little bit of wiggle room before something fails. We'll kind of look at an example of how we might use this concept. In this example, we're given a stress strain diagram and a loading diagram, and we want to know what is this distributed load, loading W, what would that have to be to make this beam here move down by 1.5 inches? And we're told that all of these bars A, B, and C that are hanging down from the ceiling, all of those bars are the same. So same material, they're all 5 feet long, and they have this distributed loading W all across the bottom there. Then we're also given the stress strain diagram. So this problem is kind of interesting in the fact that if we think about how the displacement of this guy is going to be, right? This displacement of 1.5 inches, what it is this entire bar moving down, right? So it's going to move down evenly by that 1.5 inches. Fully moves down because of this evenly distributed load W. Right? There's no, no abnormal, no one-sided loading that would cause it to tilt one way or the other. The whole thing moves down at once. So we look at our free body diagram for that. We have FA, FB, FC, and then if we were to hypothetically simplify that distributed loading, it's on the bottom there, the resultant force would be right in the center, right, because it's a rectangular distributed load. So this would be W times 8. 8W for the 8 feet across that it goes across, right? So whatever that loading is, 10 pounds per foot or whatever it is, multiplied by the amount of feet is 8 feet. So this would give us a loading of 8W. And we could use our knowledge of statics to go ahead and figure out how these forces relate to each other, right? So for example, if we took a moment about B equals 0, means we wouldn't need to account for FB or the 8W. We would get negative FA times 4 plus FC times 4 equals 0. And this tells us that our FA equals our FC, which makes sense, right? This entire thing is perfectly symmetrical. We would expect that our FA equals our FC, right? And by that same token, since our displacements are the same for everything, every bar has the same cross-sectional area, it's the same material, same modulus of elasticity. For all these reasons, we can also say that not only does FA equal FC, but it also equals FB. Right? These three forces are going to be equal because of their same displacement, modulus of elasticity, even their perfectly plastic region follows the same linearity if they're in the plastic region. Length, area, all of those things are contributing to these being the exact same. So that means that we can simplify this when we do our statics equation, Fy. Really what I have is a force plus the force plus a force minus 8W. So what I get here is 3F equals 8W, or F equals 8/3 W. Right, so now what this has done is this has really simplified this statically indeterminate problem that I have here. I was able to, from the statics and from looking at it, simplify some things down. Instead of having these 3 unknowns, I have just 1 unknown plus the W, right? So 2 unknowns. So instead of having 4 unknowns, I actually just have 2 unknowns, the F and the W. Since all of my forces are the same here, it's perfectly symmetrical, moving down through the same displacement. So now I can apply my strength of materials knowledge. I've gone through all of my statics. I'll see what other relations I can use, right? I know the displacement that I want. I know the displacement I want is 1.5 inches, and I have an initial length. So with that information, I know my strain equation, that displacement over that initial length. 1.5 over that initial length is 5 feet. 5 feet in inches is 60 inches, right? 5 times 12 is 60. So I have 1.5 over 60, punch that in my calculator. I get 0.025 inches per inch. Remember, I'm trying to find that W. So what I'm going to do is use my strain here, as well as my stress strain diagram. Try to find my loading that would cause, right? Trying to find that stress that would then I can use to calculate that loading. So for a strain of 0.025 inches per inch, 0.025 is going to fall somewhere between these two values, my 0.0012 and 0.2. So somewhere in here is my 0.025 strain value, and I'll need to calculate that stress value. And the way I can do that is with something called interpolation. If you haven't seen this interpolation concept before, essentially it's like you're taking the slope of this line and then comparing it with the values that you do know to find your unknown value. So what I'm going to do is take the values that I do know, the 60, the 36 for stress, the 0.2, the 0.0012 for strain. I'm going to set up an equation with those. I'm going to say my slope, essentially, 60 minus 36, those are my 2 stress values, over 0.2 minus 0.0012. Those are my strain values that I was given. I can use this to essentially get a slope of that line and say, okay, this equals the stress value I'm interested in, the thing that I don't know, minus 36 over the strain value I do know, the strain value that I want, right? This 0.025 minus my marker, my benchmark value of the 36, and then minus that 0.0012. Essentially what this does is it creates a slope for you to benchmark off of, and then you can use your benchmarking slope with the strain of interest, right? One of your points of interest, to back calculate the thing we're really interested in, which is this stress value here. So this is a process called interpolation, which you've probably seen in some of your other engineering classes, but in case you haven't, this is what it is. It's using this to find a point on a line when you are only given 2 points on that line. So we can find this point of interest if I go through and calculate using these values, using this equation setup. I can get a stress value of, punching that in my calculator, 38.9 KSI. 38.9 KSI. And then of course I can say, all right, my stress is force over area, which means that my force needed is going to be 38.9 times the cross-sectional area it gave me, was 0.75. 0.75. So the force needed for each bar there would be 29.2 kips, which I can then back plug in into my statics. Boop, that right there. So that I can solve for W. So my distributed loading would be 10.9, just plugging that in and multiplying by 3/8. 10.9 kip per foot. I know it's per foot because that 8 was 8 feet that we were multiplying by. And my F was in kips. So I get a distributed loading of 10.9 kips per foot.